Okay, good day. This is Math 130, Intro to Statistics. I'm Professor McCulley. This is lesson number 20 in confidence intervals for population mean where the standard deviation is unknown. So let's get right to it. So today we are going to interpret a t-distribution and use the t-distribution table. Our table is going to be actually on our calculator. And then we're going to construct and interpret a confidence interval for population mean when the standard deviation, and that standard deviation is the global standard deviation, is not known. So when your global standard deviation is not known, you are going to follow a t-distribution. So if the distribution of a random variable is approximately normal, then the t variable, the t statistic, is going to be the sample average minus the global average over the standard deviation of the sample divided by the square root of the number of elements in the sample. And this is called a t-distribution, where S is that sample standard deviation. And if you recall on the graphing calculator, if we have to do it from, if we have to calculate it ourselves from our sample that's given, remember that's going to be the SX value. All right, so a couple quick notes here. The critical values of t are denoted by t of c. The mean, median, and mode of a t-distribution, the standard t-distribution, are all 0. The t-distribution is bell-shaped and symmetric about the mean. The total area under the t-distribution is equal to 1. The tails in a t-distribution are quote-unquote thicker than those of the standard normal distribution, so it looks similar, but they're not exactly the same. And the standard deviation of a t-distribution varies with the sample size, but is greater than 1. If the t-distribution is or the t-distribution is determined by the degrees of freedom, and the degrees of freedom are calculated by the number of elements in the sample minus 1. And as the degrees of freedom, there should be no space there, sorry about that, let's fix that right now, of freedom increase, the t-distribution approaches the normal distribution, especially after degrees of freedom equal to 30 to standard normal distribution. All right, so the margin of error in a t-distribution is going to be similar to the margin of error, except instead of the z statistic, we're going to use a t statistic. And so we're going to have to calculate that t-statistic, and it is the sample standard deviation divided by the number of elements in the sample. So if we're constructing confidence interval with the mean population with the global standard deviation unknown, we're going to verify first that the global standard deviation is unknown and the sample population is either normally distributed or you have a sample size greater than 30. We're going to find those sample statistics of the number of elements in, and this is X bar, so the sample average, and then the standard deviation of the sample. We're going to identify the degrees of freedom, the confidence level C, and then the critical value T, which we'll have to calculate, and we'll do that with our graphing calculator. I'll show that in a moment. We're going to find that margin of error, and then to find the right and left endpoints of the confidence interval, we're going to add this element to the average, the mean value. All right, so first thing we want to talk about is how are we going to find that T of C so that we can plug it in to this equation here. It's a little bit different. So if we have a confidence interval, which we're going to say is a 95% confidence interval, and we have an n size of 16. Now, when we're using a calculator, or our sample size is 16. Now, when we're using a calculator, it's going to do it for us, but just as a review, the degrees of freedom are equal to n minus 1 equal to, it's going to be in this case 16 minus 1, so our degrees of freedom for this one is 15. All right, so we're not going to use that. But the calculator function that we're going to use is the inverse t. So INVT is the function that we're going to use. And since we know all of this stuff, it should be fairly easy for us to actually calculate that stuff. And so let's go let's see here. It's in the distribution, so I have to go second and then distribution, and you see inverse t right here. So I'm going to hit 4 for that inverse t. And so let's go back because I've already forgot. So a 95% confidence interval. So if we want to find the positive value for a 95% confidence interval, we have this 2.5% in the lower limit. We have the 95% total, and then we have 2.5%. So if I go from negative infinity here all the way up to here, my total area is actually going to be 95% plus the 0.025%. So this point right here, as far as total area goes, is 0.975, and so that I can put that in there. So my area is 0.975 to get that, and I guess they do want the degrees of freedom. We've calculated that to be 15. We're going to hit enter, and so in this particular instance, our T sub C, our critical value for this one, is 2.1314. 2.1314. So we have a T of C is 2.1314. Okay, and let's move on. All right, so here's an example of how we're going to do this. The members of a triathlon team record the number of hours per week spent in a pool training for a swimming leg of a triathlon. Assume that the hours spent in training is normally distributed for all of the members, not just the 16 that we are calculating for. And so the first thing that we need to do is find the sample mean. And so I'm going to use the graphic calculator to find that, and then we'll find the sample standard deviation. We'll use the calculator to find that. We've done that before, so the first thing that we want to do is we're going to clear out the list for what we had before. So I don't need the second, I just want to hit stat, and then we need to clear list, and then we just need to clear the first list. So L1, we're going to hit enter there, it's done. Now hit stat, we're going to edit, and I have the data from this page here on the other side. And so I have 5, it was 7.5, and then it's 6, and then it's 8, and then it's 10, and then it's 9.5, and then it is 7.5, and then it is 8, and then it is 5, and then it is 6.5, and then it is 8.5, and then it is 9.5, and then it is 10.5, and then it is 8, and then it is 9, and then it is 7, and I think I missed a number. Uh-oh. Because I've got 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So I missed one. I gotta figure out which one it is before we move on. I'll get it. 7.5, 6, 8, 10. I missed 8.5 right at the beginning. That's okay. And again, it doesn't matter what order you put these in. So I need an 8.5 to get the correct value. Now I've got 16. That's good. Okay. So stat, we're going to go over to tests or calculate. We're going to calculate our first variable stats. And if you have your frequency list here that has an L2 in it, I want to make sure you get rid of that. So we'll calculate this stuff. And so our average is 8.0625. So for number 1, we're going to find that sample mean. It was 8. Let's put it down there, right? For 1, we have our sample mean to be 8.0625. Our sample standard deviation, S of x, x sub x, was 1.4818. 1.4818. 1.4818. All right, and so the next thing we need to do, number 3, we need to construct that 95% confidence interval for the population by hand. And to do that, before we can do anything else, we need to figure out what that critical number t is so that we can find this margin of error. So we need this t statistic. And so to do that, again, we're going to use the inverse t function. So inverse NVT. And this one, it's going to be, let's see here, it's 95% or 99%. So to get that, it's 99%. But again, if I make a real quick little diagram here, right, and this here is 99%, that means there's 0.005 and 0.005% in each side, because that's one would be 1%. So this to this point right there would be 99.0 or 0.995. I'm sorry, I don't want to make it 99 because it's 99%. All right, so this is again 0.99 is the area underneath between those two lines, and so from negative infinity to here it's going to be 0.995, and so that leaves that 0.5% up there. All right, and then our degrees of freedom will be 15. So I've got 0.995 and degrees of freedom 15, and that'll give us, so let's see here, second, distribute, so 4, and so this time I need 0.995, I hit enter, 15 degrees of freedom. We're going to paste that in, and I get 2.9467. So, oops, sorry about that. 2.9647. All right, so now now that I've figured out what and this is my critical T sub C, I can find my margin of error, which we recall from the previous one is T of C times the standard deviation divided by the square root of the sample size. So it's 2.9647, and then the standard deviation I'm just taking from right there, so 1.4818 over the square root of 16, and I've done that calculation already, and it's 1.0916. So you can put that in your graphing calculator and that's what you'll get. And I made a slight error here that I've already caught, and you probably have caught it too. I said that T of C was this value, and I wrote a 9 there, so it should be 2.9647. That's where I got there. And so now we're going to do our, extend the page a little bit. So we're going to take our mean value, which we calculated to, did they give us a mean? Nope. So we're going to take the mean value that we have, and we're going to take that, and we're going to say that our global mean is going to be somewhere between the sample mean minus the margin of error and the sample mean plus the margin of error, which in this case is going to be 8.0625 minus 1.0916. That is my global mean. And so 8.0625 is a decimal place right there, plus 1.0916. And that turns out to say that we are 99% confident that our global mean is going to lie somewhere between 6.97009 and 9.1541 if we do that addition. All right, so how do we find that interval using technology? So for number 4, we're going to use the T interval function. And so if you go second, and then think it's in the stats. It's actually in the stats over in tests. And there's our t interval is the 8, so we're going to hit 8. And so again, we want it to be on stats. We want to figure out our, and this is from a different calculation, so we're going to change it. And we had 8.625, and then we want our that is our standard deviation that we calculated, with n being 16, and then our C level isn't 90% confidence, it's a 99% confidence. And so we can hit enter again, and 6.9709, 6.9709, and then 9.1541, 9.1541. So just to reiterate, and this is for people with the TI-83s. So if I hit that stat, I go over to calculate tests, and we're going to do the t interval. So number 8, we need it to be x bar, s sub x, and then n sample size, and then C level to plug in, and we get that value. All right, so the last thing here is we want to determine which of the following needs a normal distribution and which needs the t distribution to construct the C confidence interval for the population mean, and discuss how you came to this conclusion. So in a random sample of 25 hospitals, patients having kidney transplants, mean wait time for a new kidney was 241 days. Assume that the population is normally distributed and that the global standard deviation is 23.7 days. And so because they say that the global standard deviation right here is 327 days, we know what lowercase sigma is. And so this one we would use a normal distribution for the C confidence level. In a random sample of 35 medicine bottles, the mean number of pills in the bottle was 99.4 pills with a standard deviation of 1.0 pills. So in this case, we know S of x because that's the standard deviation of these sample pills. We don't know what the global standard deviation is. And since we don't know what that is, that tells us that we are going to use a t distribution for this one. All right. That comes to the end. So our Marvel fun fact of the day, the AI in Spider-Man suit in Spider-Man Homecoming is voiced by Jennifer Connelly, who is married to Paul Bettany, who plays Jarvis, the voice of Tony Stark's Iron Man AI. So another little Marvel Easter egg. These two are married in real life. So Tony's AI is voiced by this guy, and Spider-Man's AI is voiced by his wife. That's all I got for today, folks. Bye.